picture on the right, we're looking at it from the lipid bilayer, and we're seeing that we're getting a good population of that transmembrane helix 6 rotating about that hinge region, giving us an idea of how flexible that hinge region is. And again, what we're looking for is that helix 6 that is most straightened out, most away from the bundle. And if we look over to our left at the, we're looking at it from the intracellular end. And I should mention that these conformations are all superimposed on their ECN because we were trying to look on the changes of that ICN. We want that ICN to swing out. So when we're looking at the IC view, we want something that's the farthest from the bundle. And I probably should have put pictures here, but if you can imagine transmembrane helix 7 and transmembrane helix 5 kind of sandwiching this helix 6. And we want something that's kicked out, but we also want something that's not going to clash into the other helices, causing torsional strain. So selected in blue is the conformation of helix 6 that we ended up choosing. Once that helix, the new activated helix 6 was incorporated into the bundle, we wanted to add loops to our bundle to not only complete our bundle, but also to explore any new interaction sites that could happen with extracellular loops maybe dipping into the binding pocket. So in order to put loops on the bundle, we used a program called Modeler. Modeler uses a template library of optimal side chain conformations derived from the protein data bank. Each loop structure is going to be given an objective function, ranking value, and these are based on steric interactions and hydrogen bonding. This, just like our CM method, we're using Monte Carlo technique that uses charm force field. The lowest energy outputs of these loops were screened, and we chose an appropriate loop and minimized it. So I'm going to talk a little bit about how we screen those. So for example, our EC2 loop, we know a lot of GPCRs have disulfide bonds that connect the EC2 loop to transmembrane helix 3, as you can see here in the yellow bond. So many of the crystal structures that we've seen have that residue that's two residues away from the disulfide bond pointing down into the bundle. Now our residue that's 2 residues away from the disulfide bond happens to be a lysine with a positive charge. So we wanted to find an output of Modeler that was obviously a low energy conformer, but we also wanted that C alpha of that second residue from the disulfide bond to be pointing down into the bundle because we may be able to get another interaction in our binding pocket with the DOX ligand. Another example of one of our Modeler outputs was the N-terminus. A lot of GPCRs, we've found recent studies that there are lipid-derived lipids that come from inside the lipid bilayer. And all those crystal structures, we've seen that N-terminus draping over the EC loops. Now, our endogenous ligand, NA-glad, which I'll be talking about here in a moment, that's one of those ligands that we think is going to be coming in from the lipid bilayer. So we wanted our an output that was low on energy, but that was draping over those extracellular loops that was going to stay out of the way of our ligand. So in this picture here, you see the dark green where our EC loops are. The light greens are just some of the Modeler outputs. And then in red, I have the chosen Modeler output that we use to incorporate in the active bundle. So once both the bundles were finished, we then began to explore the binding pockets. We chose 5 antagonists and 1 agonist. And what we noticed when we docked, and I'll talk about this again a little later, is that there is a pattern in which their glide scores that we're going to be, I'll talk about, is going to correlate to their EC and IC50 values. And I should mention that these antagonists are going to be we're going to be binding those in the inactive bundle, and we're going to be binding that agonist in that newly modified active bundle. So before we could dock these ligands into their bundles, we needed to do a conformational search. And we did these on the antagonists because they were small molecules with very few rotatable bonds. Because of this, we were able to use a program called Spartan. In Spartan, we built the antagonists, optimized them, and then we took the first torsional angle and we rotated 360 degrees in increments of 51.4 degrees. This gave us 7 conformers. All 7 of these conformers were energy minimized using Hartree-Fock method at the 631 G-star level of theory. Any of these conformations that were too high in energy or were duplicates were eliminated, and we only kept the low energy and unique conformations. Once we did that, this process was just repeated. We just moved on to the next rotatable bond. So you can imagine that these conformations that are coming out are going to be exponentially growing, because imagine we take one bond angle and we rotate it and we find 3 unique conformations. Then we take those 3 conformations, go to the next bond, and we rotate each of those, and then we're getting 3 conformations for each of those, giving us a total of 9 conformations. So you can imagine how many conformations are going to happen when you get 6, 12, 20 rotatable bonds. So we can use Spartan for small molecules like this, but when it comes to more flexible bonds, that's when we have to use conformational memories method. After we had generated all the conformations for all the antagonists, we then took all the conformations of each of the 5 antagonists and we docked them into the inactive bundle using Glide. Glide generates a grid from that centroid of the select residues inside the binding pocket. Once it creates that box, we then are able to explore that binding pocket and find the lowest energy ligand-receptor complex. And Glide denotes energy favorable docks with a low Glide score. So if you see a low Glide score, that's ultimately going to be a good dock. And it generates these Glide scores based on 2 factors. It's going to base these on van der Waals and electrostatic. Thanks. Got one. Okay. So the first antagonist we used was 01918. I'm going to denote these as antagonists 1 through 5 just for simplicity. But antagonist 1 had 2 rotatable bonds, which generated 2 conformations. We can see in the picture to the left the global minimum in the green conformation, and then we can see the second conformation in pink. And just by rotating that allylic group, we're seeing an energy change of 1 kilocal. Just kind of giving you an example of what it's doing. So when agonist 1 was docked into the bundle, we saw that it was interacting with this arginine 542. This arginine 542 seems to be the primary interaction site for all of our antagonists. And with antagonist 1, we're seeing the electrons in that aromatic ring interacting with that arginine, creating a cation-pi interaction. What this does is it keeps that antagonist on that side of the bundle. Most importantly, I talked too fast for my figures. It's going to give us a Glide score of -689. But most importantly, it's keeping that antagonist at that side of the bundle right on top of that toggle switch. So if we can see that antagonist sitting on top of this toggle switch, it's stopping those antagonists from switching in their conformational change. So this is preventing that activation of that receptor, exactly what an antagonist is supposed to do.